We're ready to talk about an optimization problem. By their nature, optimization problems are word problems like related rates are. However, in an optimization problem, there's some quantity that we're trying to either maximize or minimize. If it's a manufacturing situation, we may be trying to maximize the volume of a food container while minimizing the cost of the materials required to produce it. We may also want to maximize volume for a particular shape because a particular shape is what is needed for storage reasons. Perhaps the top and the bottom of the can are more expensive because we stack cans one on top of each other. How can we then minimize the cost for a given volume? How can we optimize the flow of air over the hood of a car? These are all situations where we may be considering how to maximize or minimize some certain quantity. Often the things we want to maximize and minimize are profit, cost, area, volume, airflow, friction. These are things that have an effect on engineering problems and physics problems and problems related to business and management. However, we're not just looking for relative extrema. We already know how to do that. In these situations, there are additional conditions on the situation. These conditions are called constraints. For example, if we're looking for the volume of a box, we know the length, the width, and the height all have to be strictly positive. Otherwise, we don't have a box. We also may have other constraints provided by the situation, special conditions that aren't normally present for that function. We need to maximize or minimize the problem under these additional conditions, these constraints. This section, we're going to discuss how to do that. Our only learning objective in this section is to learn how to work optimization problems. I'm going to share my screen now so we can get started. We're going to look at solving optimization problems under two conditions. The first condition is the one that is more normal or more typical when we have a closed and bounded interval over which we're evaluating. Because it's a closed and bounded interval, we'll be able to use the extreme value theorem, which guarantees that we must have both an absolute maximum and an absolute minimum on that closed bounded interval. At the end of this section, we'll also take a look at solving problems in a situation where the interval is not closed or bounded. In these situations, we're no longer guaranteed that an absolute extremum exists, but many situations still have them, though they're not guaranteed. What we want to solve is what's called an optimization problem. When we say we're trying to optimize a quantity, we're saying we want to either maximize it or minimize it. Optimize is sort of a generic term that means both. The objective function is the one in which the quantity we're trying to maximize or minimize is represented with other variables. Let's say you're trying to optimize volume, and you'll have an equation that has volume in it related to some other variables. Or maybe you're trying to maximize the area of a garden or a pen for horses. In that case, it will be related to other variables in the problem. Those variables may have constraints. For example, if you're building a pen, you may only have a certain number of feet of fencing. That gives you a constraint on how large a pen you can build. The constraints are equations that give restrictions on one or more of the variables. It could be on the quantity you're trying to optimize, but more likely it's on the related variables in the equation for the objective function. When we think about building a box, as we mentioned before, length, width, and height must be strictly positive. They can't be zero, and they can't be equal to the volume of the box. On the other hand, we know time has to be positive. There are some restrictions that come naturally, and there are others that are imposed by the particular situation. In this section, we're going to follow a problem-solving strategy in order to approach these problems. Let's take a look at the first part. In step one, we're going to define all the variables. We're going to read these the same way we did the related rates problems. We'll read through one time to get a vague idea of what we're talking about. The second time, we'll go through, we'll cut it apart into the parts of speech, the subject phrase, the verb phrase, prepositional phrases, subordinate clauses, punctuation, conjunctions, anything that would cause a natural break in the words. If you're not great at English grammar, we go about every 2 to 3 words and we try to write something down. What we're going to be writing down are the variables that are in the problem. We're going to draw a figure if at all possible, and we'll label all the variables that are mentioned or that might be involved in the situation. Then we're going to determine which quantity is the one we're trying to optimize. And are we trying to maximize it or minimize it? In our third step, we'll look to see if we can find any constraints on the variables in the problem. It may or may not be able to be determined at this time, but most of the time you can find at least a few constraints on the variables in the problem. Then we're going to take the quantity we're trying to optimize and relate it with an equation to the other variables in our situation. This is the objective function, when we relate what we're trying to optimize to the other variables involved. The formula will typically involve multiple independent variables. This is a problem for us because we work in single variable calculus in Calculus 1. We're going to have to rewrite the equation somehow so that we can get the quantity we're trying to optimize written in terms of only one independent variable. In step 5, we're going to use the equations relating to the constraints. We're going to write these down, and we're going to use them to rewrite the objective function in terms of one variable only. You'll have to have some constraints that relate the variables together. In this case, we're not necessarily talking about the one we're trying to optimize. We're talking about the others. We'll get an equation that relates them, solve for one of the variables, and substitute into our objective function until the objective function is only in terms of one independent variable. Then we're going to identify the domain of consideration for the one variable that's left. What values might come out? We need to think about this because there may be some constraints set by the physical situation that the problem is set in. Our last step here at the bottom is to locate the maximum or minimum value of the function we found in step 5. The equation the equation that is a function of one variable and is related to the quantity we're trying to optimize. We're going to do this by finding the critical values using the first derivative, and then we'll either use the second derivative test to determine if they're maximums or minimums. And we'll go back to the problem to see what it was we were trying to solve and fill in any blanks we may have. This is pretty much everything you have to learn in this particular problem, except that you need some experience now in setting these problems up. So I'm going to model this for you now. We're going to read it one time through just to get a vague idea of what kinds of formulas might be important. A rectangular garden is to be constructed using a rock wall as one side of the garden and wire fencing for the other 3 sides. Given 200 feet of wire fencing, determine the dimensions that would create a garden of maximum area. What is the maximum area? What I got out of this is we're trying to build a garden, and I did catch that we wanted to maximize the area. However, I did note also that we only have so much fencing and that we're going to use a rock wall for one side. I've already pasted a picture in here for you, and let's go ahead and start labeling the pieces in this picture as we go back and read through it one more time. A rectangular garden. If you don't have a picture, you should now be drawing a rectangle. Is to be constructed using a rock wall as one side of the garden. Well, this is my rock wall. So I've got a rock wall here. I won't need fencing on that side because I've already got the rock wall. And wire fencing for the other three sides. Okay, then this side is wires. And this side is wires, but it connects to the rock wall. Given 200 feet of wire fencing, you should stop and write that down. 200 feet of wire. Determine the dimensions. Well, I've got a rectangle, so the dimensions would be the length and the width. They're already labeled in this picture, the length being y and the width being x. I'm to determine the dimensions, so I want to find length, which equals y, so I'll put a blank. And I need to find the width, which is x, and I'll put a blank. That would create a garden of maximum area. This tells me that I'm trying to maximize the area. This is my objective. I'm trying to maximize area. I want it as large as possible, but subject to the constraint that I use one side as a rock wall and only 200 feet of wire fencing. The last sentence is, what is the maximum area? So I'm also looking to find what the maximum area is. Make sure you draw a blank so that you know you have to fill that information in at the end. Now that we've gone through and we've defined all of our variables, we've drawn a picture, we've determined what quantity we're trying to optimize, and we've looked to see what our answers should take, what form they should be. We need to determine if we have any constraints on x and y. X and y will be in the equation with area. In fact, we know what the equation is. We can write it now. We know that area is equal to length times width. So we have A equal to xy. I need something to replace one of these variables because this is an equation with two independent variables. It's got to be broken down into one. So come back over to the problem, look at your picture, and look at the information that you were given. In this case, I know that x plus y plus x again must equal 200 feet. If I use less than 200 feet, I'm not maximizing the area. So my constraint equation is given by the perimeter of the three sides where I use wire. 2x plus y equals 200 feet. Now it's easiest in this particular problem to solve for y because I want to avoid the fractions. So I'm going to solve for y in the constraint equation, and then I'm going to replace y in my objective function. This is my objective function here. I'm going to be writing area as a function of x. The next thing I want to do is go ahead and simplify it. I now have area as a function of x. 200 feet times x minus 2x squared. Notice that the units would be square units. Feet times x is in feet, so it gives me square feet, and x is feet, so x squared is square feet. So I feel pretty confident that I may have set it up correctly. Now, the next step that we want to follow after getting a single independent variable in our objective function is we want to optimize it. In that case, we're looking for relative extrema. So in order to find the relative extrema, we're going to go ahead and take the derivative of the area function. Keep in mind that both x and y have to be strictly positive. They cannot be 0. In addition to which, they are obviously less than 200 feet. Let's go ahead and take the derivative of area so we can find the critical points. We can also add to our constraints by writing x has to be greater than 0 and less than 200 feet, as does y. Now let's look at critical points. The derivative of a with respect to x is 200 feet minus 4x. To find the critical values, we set this equal to 0. Or we look for where it does not exist, but the function does. However, in this case, there are no places where it does not exist because the derivative is a polynomial. When we set it equal to 0, we get that 200 feet equals 4x, or x equals 50 feet. We have found the value of x in order to make it be something, but we don't know what that something is. There's no guarantee that this sets it up to be a maximum. We simply know it's a potential place for an extrema value. We can either do the first derivative test and test for increasing, decreasing to find whether it's a relative minimum or maximum, or the second derivative test. In this case, because the first derivative is relatively simple, we're going to do the second derivative test. To do the second derivative test, we find the second derivative of the area, which turns out to be -4. That means that it's always concave down because the second derivative is always negative. Since it's always going to be concave down, then it must be concave down when x is 50 feet, which turns this into a relative maximum. Now, I'm not done until I've answered all the questions. So far, I've identified that the width is 50 feet. Now it's time to find the length. Go back to the constraint equation that you had originally that you see here and solve again for y, and then substitute 50 feet for x. You can do this one in your head and you'll come up with 100 feet. Make sure that they do add up to 200 feet. We need twice the width and 1 times the length, and that gives us the 200 feet of fencing. I'm still not done until I've found the maximum area. But the area is given by x times y, which is going to give me 5,000 square feet. In example 2, we're constructing a cardboard box with the dimensions 2 meters by 4 meters. You then cut equal sized squares from each corner, so you may fold the edges. What are the dimensions of the box with the largest volume? About all I got out of it was box and cardboard, and I'm cutting. I found over the years that this problem actually causes students some anxiety, and they don't really know how to do it. So imagine, if you will, that you have a piece of cardboard And you're going to turn this into an open topped box. It won't have a lid. You take a pair of scissors and you cut corners out of each of the 4 corners. What you end up with looks like this. When you're looking at this, notice that this distance is X and this distance is X. You've cut squares out of each of the 4 corners. What you're going to do next is fold the 2 end sides and the 2 other sides and tape around the edges to create this open topped box. Now that you understand the situation a little better with the help of a visual, let's take a look at the graph and the picture. We're going to go back and break apart the words and start labeling our picture. We actually have several pictures to help us. You are constructing a cardboard box, I think, rectangular box, with the dimensions 2 meters by 4 meters. Okay, so the box originally, before you cut it up, the original piece of cardboard was 2 meters by 4 meters. This is before I cut the corners off. So it's 4 meters this way and 2 meters this way. You then cut equal size squares from each corner. Each corner is labeled with the X on each side of the square, so that you may fold the edges. What are the dimensions of the box with the largest volume? Well, the dimensions of this open top box will be length, width, and height. So I'm looking for length, width, and height. If I think about what I'm doing here, remember that this cutout is length X on each side, and I'm going to fold that side of length X straight up so that it becomes the height of the box. Well, in that case, I kind of know what my height is. My height must be X, the size of the square I cut from each corner. I want to optimize volume by making it as large as possible. So my objective is to maximize the volume. I've read through the words several times, and I think I have everything written down. I've labeled my picture, but I don't have any constraints, and I haven't written the objective function yet. What would the objective function for this be? In this case, I need to relate the volume to the length, the width, and the height X. My objective function, off there, is volume equals X times L times W. Now I know I need to replace 2 of the 3 independent variables using some kind of constraint. So let's see what the constraints on these different things are. Let's first start with X. We cut corners of length X from the sides. Well, if I start with X, how big of a corner could I cut? Well, if I cut so that X was 2, it would split the length in half, which means I wouldn't have a box. So I know that X has to be less than 2, and I know it's got to be positive. Let's look at the other side. If I look at the other side, at the width is 2 meters. If I made X 1 meter, it would cut that completely in half, and again, I wouldn't have a box. So in fact, X not only has to be less than 2, it has to be less than 1. Now let's go ahead and write an expression to represent the length of the box after we folded up the sides. Not the original rectangle, but the finished box where we folded everything together. This length lost 2x. It started 4 meters long, but it lost 2x. So I know my length is going to be 4 meters minus 2x. Notice that this also gives you a restriction on x. X can't be larger than 2, or the length would be 0. Now we write an expression for the width. The width started 2 meters, and we lost 2x from each side as well. One from the top, one from the bottom. And this also gives you the other restriction. X can't be greater than 1, or your width would be 0. I know that the length and width both have to be between 0 and 4 for length and 0 and 2 for width. They're not going to be the full size because I did cut something from the corners. So I have restrictions that the length has to be strictly positive and less than the 4 meters, and the width has to be strictly positive, but less than the 2 meters. Do I have the ability to solve for two variables in terms of the same one? It won't do any good to solve L in terms of W and then solve W in terms of X. We want to have only one variable in the objective function. In this case, L is written in terms of X and W is written in terms of X. So we can substitute those in place of L and W in the objective function. This gives us X times 4 meters minus 2X times 2 meters minus 2X. We should probably go ahead and multiply it out because we know that we're going to want to optimize it. That means find relative extrema. When you multiply this out, you get that the volume as a function of the height x is 4x cubed, which would have cubic units, minus 12 meters x squared, which would also have cubic units, plus 8 meters squared times x, which again has cubic units. When the units work, you can feel more confident that you have it set up well. We've now got the objective function written in terms of one independent variable, so it's time to find the relative extrema. To do that, we're going to look for critical values. So I take the derivative with respect to x to get 12x squared minus 24 meters x plus 8 meters squared. I set it equal to 0 and solve. The first thing to realize is that there's a common factor here of 4. You could divide everything by 4 to make solving this a simpler situation. Let's go ahead and do that now. Unfortunately, when I get done, when I look at this trinomial here, I can't see any way to multiply 3 and 2 together but end up with a negative 6. I can get a negative 7, but I can't get negative 6, which tells me I need the quadratic formula. You may want to pause the video to work it out, then turn the video back on and compare. So let's see how you did. When you apply the quadratic formula, you can leave the units in. Notice they do work out. If they don't, something's probably wrong. We end up, after simplification, with 1 meter plus or minus the square root of 3 divided by 3 meters. We split this into 2 so we can get approximate values. And this gives me about 1.6 meters and 0.4 meters. Now I have to decide whether these are extrema values at all. To do that, I'm going to apply the second derivative test. It doesn't always work. If I get 0, I'll have to use the first derivative test. But if it works, it's often less work. I rewrote the first derivative so that we could more easily take the second derivative. This gives me 24x minus 24 meters. When I look at this, I need to evaluate this at my two different values. If I substitute 1.6-ish in for this, it's going to make this larger than 24. So at this value, it will be positive. What does that tell you? That tells you that it's concave up. If it's concave up, this must be a relative minimum. But I'm looking to maximize the volume. So I need to evaluate the second one at the second derivative. When I substitute 0.4 in here, it makes the first term smaller than 24, which causes it to be negative. Because it's negative, I have a relative maximum, which is what I'm looking for. It doesn't mean that the 1.6 didn't solve the problem. It just doesn't solve the application problem that I'm trying to work. So the one I'm looking for is 1 minus square root of 3 divided by 3. Let's go back and remind ourselves of what it was we were looking for. We have the value for x, which is 1 minus the square root of 3 over 3 meters. We also wanted the length and the width. To find the length and width, we need to replace the value we found for x into the two constraint equations. Let's go where we have some room and do that. My constraints were as follows. The length was 4 meters minus 2x, and the width was 2 meters minus 2x. Substituting the value of x and solving will give us the following solution. Depending on your instructor, they may prefer an approximate answer or they may prefer the true answer. Or like me, they may ask for both. Be sure that you can find both values. We were not actually asked to find the maximum volume. We could, now that we have the dimensions, but we're not required to by the problem. Let's now turn our attention to the next problem in the set, which is problem number 3. Example 3 and example 4, which relate to the same situation, are probably the two most difficult examples in this video. Let's read through it together. To carry a suitcase on an airplane, the length plus the width plus the height of the box must be less than or equal to 62 inches. Assuming the base of the suitcase is square, show that the volume is given by this expression, height times the quantity 31 minus half the height, the quantity squared. What height allows you to have the largest volume? I got that we're talking about a suitcase and that I'm trying to prove a formula, and I'm also looking for something else which didn't stick with me. Let's go back and we'll start drawing a picture, finding variables, and labeling them. To carry a suitcase on an airplane, the length plus width plus height of the box, length plus width plus height, must be less than or equal to 62 inches. That gives me an inequality which we've not seen before. Well, not an or equal to one. assuming the base of the suitcase is square. Square. Well, the suitcase is built like a rectangular box. So if it's square, I must have something like this. Let's see if I can draw this well enough. There we go. Now, if it's square, then the length and the width must be equal to each other. Well, then I can rewrite that constraint equation in terms of only one of them. I'm going to choose L and write 2L plus H must be less than equal to 62 inches. Okay, I got that. Back to the words. Show that the volume, okay, is this formula. Show V equals the height times 31 minus the height divided by 2 all squared. Well, that must mean that I left height in the equation and that I took L out of it and W. Then it says what height allows you to have the largest volume. It's not the height I'm trying to optimize. I'm trying to optimize the volume by maximizing it. So I want to maximize volume, but I want to find the height that makes that possible. I need an equation that relates the length, the width, and the height of the box to the volume. Well, I know that the volume of a box is given by length times width times height. In this particular situation, I'm trying to make it as large as possible. So it makes sense to use as large of dimensions as I can, which means 2L plus H equal to 62 inches. Let's take our constraint now and rewrite it to get rid of L. I would normally have chosen to get rid of H because I like to avoid or solve for H because I like to avoid fractions. But we know we have to leave H in the problem because the equation we're trying to prove has only H in it. That means L has to go. Now that I've rewritten L as 31 inches minus H over 2, I'm starting to see where this equation might be coming from. I remember that L and W are the same width, so I can rewrite the objective function in terms of L and H only. This would give me L squared times H, or I could write H times L squared. Then when I substitute for L, I get the equation I was trying to prove. I've done the first part, so now I turn my attention to maximizing the volume. I have taken my objective function and reduced it one variable at a time until I have it in terms of only one variable. Now it's time to go ahead and take the derivative so that we can find the critical points and relative extrema. In this case, you can either multiply it out and then take the derivative, or you can use the product rule and the chain rule. I don't know that one is going to be better than another, but I believe that I chose to multiply it out. When I multiplied it out, I got, for the inside, 961 square inches minus 31 inches times H plus H squared divided by 4. When I distribute the H, I get 961 square inches minus 31 inches times H squared, oops, lost my H there, plus H cubed divided by 4. Now I can go ahead and find the critical points by finding the derivative and setting it equal to 0. This is going to give me 961 square inches minus 62 inches times the height plus 3/4 h squared. This, of course, is going to be a quadratic equation. And the first thing that I would probably do would be, when I set it to 0, would be to multiply by 4 so that I can get the fraction out of there. Or you can stay with the fraction and just know that you're going to have to deal with it. In this case, I have no idea if it factors or not, but even if it does, I probably won't be able to find it very easily. So again, I'm going to use the quadratic formula. Pause the video so that you can work it out, then turn the video back on and we'll compare our results. So let's see how we did. I went ahead and set the equation equal to 0, and then I solved it. Notice that I did use the quadratic formula and I kept the 3/4 since I thought maybe I'd get some cancellation, and I did. As it turns out, I end up with the square root of 961, which is a perfect square. It turns out to be 31 squared. This gives me two possible answers, 62 inches and 62/3 inches. But let's go back to the situation and think about what we're saying here. We know that the length plus the width plus the height must be less than 62 inches. How could the height alone be 62 inches and still have a box? Well, it can't, which means that that one will not be our solution if there is one. There may not be one. Let's go back now and look at the second one. The second possibility is 62/3 inches, which is just shy of 21 inches. In order to evaluate if it's a relative extrema, I'm going to apply the second derivative test. To apply the second derivative test, you must find the second derivative, which in our case becomes 3/2 h minus 62 inches. Now I'm going to evaluate that at the one that I think is a possibility. When h is 62 thirds inches. And this gives me 3/2 times 62/3 inches minus 62 inches. When I multiply this out, I end up with 31 inches minus 62 inches, which gives me a negative 31. I'm not interested in the number. What I'm interested in is the sign. It's negative, which tells me it must be concave down. Because it's concave down, I must have a relative maximum there. And that's what I'm looking to do, maximize the volume. So I know the height that makes it possible is 62/3 of an inch. Going back to the original problem, that's all I was asked to find, so I know I'm done. If I were asked to find the length of the width, I could do that by going to my constraint equations. Now, let's take a look at example number 4, the other more difficult problem in this section. Let's read through the problem together. To carry a suitcase on an airplane, the length plus width plus height of the box must be less than or equal to 62 inches. This is the same as in the previous problem. Assuming the height is fixed or constant, show that the maximum volume is still given by the same formula as in the previous problem. Well, that is different because now we're saying that the height is a constant, which means it's not a variable, but somehow I've got to show that this formula still applies. What height allows you to have the largest volume? Well, they must have changed things again because if they're asking for the height, well, that must mean that it's varying, so it's back to being a variable. This time, we do not assume the base is a square. We can assume that it is a rectangular parallelepiped, otherwise known as a rectangular box. Let's go ahead and break down what we have and represent it on the picture and in words. To carry a suitcase on an airplane, the length plus width plus height of the box must be less than or equal to 62 inches. Assuming the height is fixed or constant, that means it's a constant number and not a variable. Show that the maximum volume, okay, I'm still looking to maximize the volume, is still h times 31 minus half the height quantity squared. Okay, I've got to show that first. Then what height allows you to have the maximum volume? Do not assume the base is a square. Okay, well, maybe I should draw another picture or label the picture that you see here. If I let this be the length and I let this be the width, then this would be the height. Again, I can write the objective function to relate the variables together. V is equal to the height times the length times the width. This time, the height at first is being treated as a constant and not as a variable. Whatever it is, it's not changing. When I do this, I want to come up with something to represent the equation. So I come up here and I look at this equation that I have at the top. I'm trying to show first that the volume is still given by this formula, which means somehow I've got to get rid of the length and the width. In this case, I can leave the height in the objective function because it's not acting as a variable. It is a constant. So that leaves me with two independent variables, L and W. Let's solve the constraint equation for L and use that to substitute for L so that the equation, the objective function, is written in terms of H, which is just a constant number, and W, an independent variable. Using the constraint equation, I can write the following. L must be equal to 62 inches minus W minus H. Putting that into the objective function leads to the next step. Go ahead and multiply it out and then rewrite it in terms of W. When we do that, notice that the only variable is W and that the minus H squared is constant, the H is a constant, and 62 inches times H is a constant. That means that we have a quadratic equation in terms of W. I'm looking to maximize the volume. I need to take the derivative with respect to W. Go ahead and pause the video, take the derivative, find the critical values, and then evaluate at the second derivative test to see what you get. Let's compare results. Also note that I forgot to write the W on the last term when I distributed, so make sure you have that there. Otherwise, it will completely tank the rest of the problem. To find the critical values, I take the derivative with respect to W, which is the only true variable in the equation. H is not known, but it's fixed. It's a constant number. When I take the derivative, I get 62 inches times H minus 2H times W minus H squared. I set the derivative equal to 0 to find critical values. Notice that this is defined everywhere in our domain between 0 and 62. So I know that there are no critical points coming from the derivative not existing. Setting it equal to 0, I go ahead and solve for W. For W, I end up with the expression 31 inches minus H over 2, which means that in my equation for the volume, which is here, I can replace the W with that expression. Now, I could substitute it in here and work it out and try to prove that I get the original. But I can also go back to the original objective function that the volume is the height times the length times the width. I know the height is H, and I now know that the width is 31 inches minus H over 2. If I can get the length in terms of H, I might find an easier way of representing the volume in terms of H only, rather than having to replace each of these W's with that expression. I come here to the constraint equation, which says the length is 62 inches minus W minus H. Let's write this down below so we can work from it. The length is given to be 62 inches minus W minus H. Again, it was set up as less than equal to, but we want the maximum volume. So we're going to push the constraint to the edge of its range. Now I know that the width is equal to this value up here. And that means that I can replace the expression for W in the expression for L. This gives me 31 inches plus H over 2 minus H, which means that my length is in fact the same as my width, 31 inches minus H over 2. In other words, if you want to maximize the volume, use a square base. Now, does this prove the statement I was trying to show? Yes. If I replace L and W, which are equal, with 31 minus H over 2, it becomes squared and then multiplied by H. I have shown that the volume is equal to that expression. So you can write, thus, volume equals H times 31 inches minus H over 2 squared. Now, the last thing we need to find is what is the actual value of H. In order to do that, we are again now looking at this equation right here and trying to find the maximum volume for H. We know H is fixed, we just don't know what it is. So what we're going to have to do is we're going to have to evaluate the derivative now with respect to H. It's almost like starting the whole problem over again. I'm going to apply the product rule and the chain rule this time. The derivative of the first factor H is 1 times the second factor unchanged. Then I'm going to add to that the derivative of the second factor using the chain rule. The power reduces to 1, and the derivative of the inside with respect to H is a negative 1/2. Then I multiply by the first factor, which is H. The 2 and the negative 1/2 will cancel, but it will give me a negative here and H multiplied by what's left. Let's go ahead now and multiply out what we have left. I have 31 inches minus H over 2 quantity squared minus 2h times 31 inches minus h over 2. Instead of multiplying it out fully, because I know I'm going to set the first derivative equal to 0, I can factor out that binomial as a common factor. This gives me 31 inches minus h divided by 2 times, well, 31 inches minus h over 2 still, minus 2h. Now I can go ahead and combine the minus h over 2 and the minus 2h and get minus 3h divided by 2. 3, 5. How much would that be? Did I do that right? Okay. Now to find the critical values. This implies that 31 inches minus h over 2 is equal to 0, or 31 inches minus 3h over 2 is equal to 0. In both cases, we know that the derivative is defined everywhere on our domain. Let's now solve for h out of each equation. In the first one, I get h equals 62 inches, which I know will not work because the length plus the width plus the height has to be less than or equal to 62. I can't put everything into the height or I won't have a box. That would actually give me a minimum volume of 0, so it must be a relative minimum. Then I can locate the other one, which gives me 62 inches divided by 3. In other words, we've just solved the same problem that we've already done previously, but from a different point of view and with different constraints. Let's turn back to make sure we've answered all the questions. It looks like we have, so we know that we're done. Let's take a look at one last example on a closed and bounded region. This will be example 5. This is example 5. Example 5 is another type of problem that is fairly typical in textbooks, but it also applies in some manufacturing and engineering applications when you have to fit a certain object in a particular space of some already known shape. In this problem, we want to find the area of the largest rectangle that fits into the triangle with sides x equals 0, y equals 0, and the line x divided by 4 plus y divided by 6 equals 1. Okay, all I got out of that was find the area of something. I can't even remember what the shape was, but I know it's got to fit inside that triangle. Let's start over and break it apart phrase by phrase. Find the area. Okay. Find the area. Area equals of the largest rectangle. What am I trying to maximize then? Well, I must be trying to maximize the area. Find the area of the largest rectangle that fits into the triangle with sides x equals 0. Well, that's just the y-axis. Y equals 0. That's just the x-axis. And this line. Well, I don't like the form of that line, so I'm going to rewrite the form of the line into a shape that I prefer better. I'm going to take this and I'm going to multiply by the lowest common multiple or denominator, which is 12. This will give me a form that I'm more accustomed to. This gives me 3x plus 2y equals 12, and I can solve this for y. and I come up with the equation -3/2 x plus 6. And that does, in fact, appear to be the case. It's coming down 3 for every right 2. So I know I've got the equation. I guess I could have written it directly from the picture as well. I want to maximize the area, but I don't really seem to have any variables other than x and y, and that's really referring to the lines. So I've got to fit a rectangle under here. Well, then let's draw one. If you can't think of anything else to do, the best thing to do generally is to draw a picture. So I'm going to draw a picture. I'm drawing a rectangle that fits inside the triangle. If I'm going to make it as big as possible, then the corner of it, the upper right corner, is going to touch that line. Well, what does that tell me? Well, that tells me that that point right there, xy, is on the line. Well, what are the dimensions of that rectangle? Well, if I want to call this the length, this would be, well, the x coordinate. And what would this be? If you want to call this the width, it would be the y coordinate. Oh, well, then this point is giving me the width of the box and the height, or the length of the box, or width and height, however you want to think of it, the two sides of the rectangle. But I know that it's on this line, so this has to satisfy the equation that you have here. So this is your constraint. I also know that x has to be greater than 0, but it can't be bigger than 4 because the triangle intersects the x-axis at 4. I know that y has to be bigger than 0, but it has to be less than 6 because the line intersects the y-axis at 6. So I have 3 constraints. It has to be on the line, and the dimensions have to fit in here. Now we write the objective function to relate area to the variables we have. Now we need to replace one of the variables with the other one. I've already solved this equation for y, so it makes sense to substitute for y. The next thing that I want to do, of course, is to find the critical values. Pause the video now, work it out, and turn it back on so we can compare our results. So let's compare results. I replaced the y with the expression from the constraint equation and got a quadratic equation in just x. Find critical values. I took the first derivative, which gave -3x plus 6, which is defined everywhere. Then I set it equal to 0 and got a possible location for a relative extrema of 2. That doesn't guarantee it is one. It could be a saddle point or a point of vertical tangency. So then I applied the second derivative test. I found a second derivative by taking the derivative of the first derivative, which gave me the constant -3. Because it's negative, it's always concave down, which means that this critical point must be a relative maximum. I was asked to find the maximum area. So in order to find the maximum area, the next thing I did was find the y value by again using the constraint equation. This gave me a y value of 3. Multiplying the 2 by 3, I got the maximum area as 6 square units. Let's now take a look up here and see if we can draw the one that actually has the maximum area. X comes out to be 2, and y comes out to be 3. This rectangle here that I've shaded in pink is the one that fits underneath that line and next to the axes, but has the maximum area. We now have only one problem left to discuss, and this last problem is not on a closed bounded region. Because it's not on a closed bounded region, we are not guaranteed that an absolute extremum exists. We have to have a closed bounded region to use the extreme value theorem. However, as we'll see, some functions do still have absolute extremum. It's just not guaranteed. Now we want to take a look at example 6. Example 6 says a manufacturing company makes right circular cylindrical cans, just a normal bean can, to transport its food product. If the volume of the can must contain 354 square cubic centimeters, what is the height and radius of the can that will minimize the surface area? Well, you would want to minimize the surface area because the less surface area, the less raw material, and that is cost. Okay, coming back to the beginning, a manufacturing company, got it, makes, okay, right circular cylindrical cans. If you don't have a right circular cylinder, draw one now, to transport its food product. If the volume of the can must contain 354 cubic centimeters, I should write that down. Volume is 354 cubic centimeters. What is the height and radius of the can? Oh, okay. Height of the can and radius of the can. Okay, I should label that. Here's the radius, and the height is going to be here. Okay. That will minimize the surface area. This time we're looking for a relative minimum. We want to minimize surface area. I don't actually have any equations yet, so let's see if we can find some. First, can I think of a way to relate surface area to height and radius? Well, I know that the area of the bottom is a circle, pi r squared, and I have another one on top, so I have 2 pi r squared. So for surface area, I have 2 pi r squared, which of course will give me the top and bottom of the can. What about the sides? It's time for another prop known as a toilet paper roll. A toilet paper roll without the top and bottom is a right circular cylinder. If you cut it and open it up, aha, it becomes a rectangle. Let's close it up again so we can see what they are. Notice that when I open it, this side, which is the circumference of the circle, becomes the length. And this side, which is the height, becomes the width. So this becomes the circumference times the height. The circumference is given by 2 pi r and the height is h. I now definitely have an objective function because I've related them together. I don't yet have any constraints. Go back to the information you're given and try to relate h and r together in such a way that you can eliminate one. I'm told the volume is 354 cubic centimeters. That means that I have to be able to write the formula for volume and have it equal 354. The volume is pi r squared h. This becomes our constraint equation. In this case, because r is squared, it would be easier to go ahead and eliminate h by solving for h. From the constraint equation then, I'm going to have H is equal to 354 cubic centimeters divided by pi r squared. This is coming from the constraint of the volume. Now that I have an expression for H, I can replace it in the objective function to get an equation in terms of just R. Go ahead and pause the video, work out the rest of the problem, then turn the video back on to check your answer. Let's compare results. I went ahead and simplified the surface area objective formula, and I dropped the R to the denominator. But to take the derivative, I'll probably move it to the numerator with a -1 exponent. Remember that H is given by this equation here coming from the constraint. When I applied the derivative, I got the formula here, 4 pi r minus 708 cubic centimeters divided by r squared. I set it equal to 0, noting that it's defined everywhere that fits the situation. It's not defined when r is 0, but a radius of 0 makes no sense to make a can. The radius and the height have a constraint that they must be strictly positive. Then I go ahead and solve for r. When you solve for r, you get the cube root of 177 divided by pi, and the units work out to be centimeters. It doesn't guarantee, however, that this is an extremum. You have to check with either the first derivative test or the second. I applied the second derivative by taking the second derivative of the function or the derivative of the first derivative. This gave me 4 pi plus 1,416 cubic centimeters divided by r cubed. Note that I don't even need to plug in the value. 4 pi is positive, r is positive, so r cubed is positive, so the second term is positive. That means that the second derivative is positive for all values of r, which means that it must be concave up, and this must correspond to a relative minimum. I am trying to minimize surface area in order to minimize cost. That means that this value for r is the one I'm looking for. Then I go back to the constraint equation where I solve for h, and I substitute my value in to get the expression for h. It's rather complicated, so I would probably just leave it like this. I wouldn't try to simplify it, though I think you could simplify it a little bit. So this brings us to the end of the material on optimizing functions. I hope that you've learned something from it and that you feel better equipped to tackle your homework problems now. Our next section is going to be a deviation from some of what we've been doing. Instead, we're going to get back into limits again when we study L'Hopital's rule. This is one of the most important sections in this course, so make sure you're prepared for section 4.8 coming up next.